And on the ACT, on those kind of tests, they will use those kind of words. So, you know, the better you do on your ACT, SAT, the more money you're going to get in scholarships. So think of it as you're paying yourself as you learn. Okay, so monomials versus polynomials. They give you a couple of examples of what something like this can look like. So say 14, 3x, 2xy cubed. These are all monomial. And the simplest definition in my blue book, or the one I like to give, is a number or a product of numbers or variables is what a monomial is. Okay, you might also think of it as a single term. You'll see that used a lot. In contrast, a polynomial is several of these slammed together with addition or subtraction signs. Say 2xy cubed added to 3x added to 14. This is all of those added together, and these would be multiple monomials put together, otherwise known as a polynomial. Specifically, Philip recognized that since there's 3 terms there, this is a trinomial. Okay, that is a trinomial. You guys learned that the numbers preceding variables are called coefficients. 2 is the coefficient of xy cubed. 3 is the coefficient of x. And what it does is it tells you how many of that particular variable thing there is. Like this is 2 xy cubes. And this is 3 x's. So that's what the coefficient does. It names how many there are. Back to this polynomial that I made up, that polynomial is simplified because all like terms are combined. When all like terms are combined, your polynomial is simplified. And the thing above cannot be combined any further because 2xy cubed is not the same as 3x. You might think, well, wait, there's an x here and there's an x here. That is true. But this is not x. This is xy cubed. This is not xy cubed. This is x. Completely different animal. So when all like terms are combined, the polynomial is said to be simplified. And that's what we're going to be reviewing today. This is a review more than anything else, is how to collect like terms, thereby adding them together. And example 1 is a very simple version of this. I'm sure you guys don't even need me to do anything with it, but I'll do an example 1 with you just to be sure. Here's my example 1. The instruction on this one is to simplify it. And to simplify it, you need to combine anything that is like. Right off the bat, I see that we have x squareds. -3 of them and +1 of them. How do I know this is +1? Because if there's no coefficient, it's a 1. Combining your x squareds is going to result in -2 of them. We also have x's, looks like +5 and -2 x's. Numerically combining their coefficient results in a +3 of them. Our constant, our number that we know exactly what it means, has no friends. He's by himself. Therefore, this has now been simplified by combining like terms. If you combine things that are not like, you are creating a train wreck. And you need to review what combining like terms looks like, because otherwise everything will be wrong and you'll be confused right off the get-go. I would also like to look at page 150 for just a second, where it says problems. Look at page 150. It looks like this. You guys have those little squares? Write the sum of the areas of the rectangles as a polynomial in simplest form. I want you to look at the first one with me. This is similar to their example 2. I just didn't want to do the exact same one that they have in the book. Their example 2 looks like this. They have a blue box, which is 2 x's from right to left and x from top to bottom. They have a green box, and I'm trying to copy it as best I can. That is 1 unit from right to left and x units from top to bottom. They have an orange, thicker looking rectangle. That is 2 from top to bottom and 2x from right to left. Looks like it matches that one. And a pink little shape. That is 2 by 1. And the instructions on the top of your book's page 150 says, write the sum of the areas of the rectangles as a polynomial in simplest form. In order to do that, you need to find the area of each rectangle. Area is defined as length times width, am I right? So if this is the blue one, what is its area? Philip, what would you say the area of this one is? 2x times x, which is what? 2xx, otherwise known as 2x. Yep, that's the blue one. The green one, what would the area of 1 times x be? Anybody hazard a guess? X. And I'm going to write positive just to remind myself. The green one is a positive x. Below that is the orange one. The product of 2 times 2x's. If I have 2 times 2x's, how many do I have? 4x. And there are positive 4x of those. That's the orange. Lastly, it looks like I have pink. Anybody know what 2 times 1 is? You are simplified when all of your like terms have been combined. Justice, have all of our like terms been combined? Yes, so x squared is different from x, which is different from x. What's the result of combining those two? Yeah. Other than that, you were right, though. There are no more numbers, otherwise known as constants, by themselves. And there are no more x squareds. That particular variable has nothing else it can combine with. X squareds are different from x's. This literally means 2 times x times x. X times x is different from just plain old x. So the question example 2 is mimicking, and what I just did using page 150 is I wrote the sum of the areas of the 4 different colored shapes. Oops, last one I forgot to write the letter above it, pink. As a sum, and then I combined the green with the orange because the green box and the orange box were both x's. The green box and the orange box were both x's. That's example 2. If you want to look at more like example 2, you can look back at page number 146 a little bit more. They give you some terminology about the word degree. The degree of a variable in a monomial versus the degree of a monomial. I'm going to show you that here a little bit. This is my example 3. If you are given a monomial, and this is a monomial, the degree of each thing is how many times it appears within the monomial itself. And if I were to break this apart, it would be 4 times x times x times x times y times z times z. Am I right? How many times does the, say again? Sorry. How many times does each thing appear? Well, we know that the 4 is only there once, okay? The coefficient is only there once. It really doesn't figure in, though, to the degree of the overall monomial. What does figure in is the degrees of the variables. There are 3 x's, 1 y, and 2 z's, which means the degree is 6. Okay? The coefficient, even though it only appears 1 time, does not figure in when you are asked for the degree. The degree is the sum of the exponents of any variables that appear within the monomial. Y is y to the first, you just don't write it. Okay? How about this one? 3z squared y, or z squared, you know what? Z squared ab to the 4th. 3 appears once, but we don't care. Yep. 2 z's, 1a, 4 b's, the degree is 7. Okay? It's all about the variables there. Okay, examples 4 and 5. Adding and subtracting. Adding is super easy. I happen to think adding is just basically combining a bunch of like terms. So, example 4, we're going to add polynomials together. And the trick to that is simply combine the whole mess. It combines the like terms. So, take 2a squared, add it to ab and 2b. Take this and combine it with 4a squared minus 3ab and a positive 9. So what you are doing is you are combining these two polynomials. Within that big long string of monomials, we have a squareds. 4 of them and 2 of them. So altogether, how many a squareds are there, folks? I see some ABs. I see a positive 1 and a negative 3. So how many ABs is that? Any other B's we can marry this with? And any other constants? Nope. This is the sum of these 2 polynomials. Subtraction, and where everybody gets bound up, is always subtraction. If I say this to you, take $5 from $10. How would you write that mathematical equation? 10 minus 5, very good. because you are taking 5 from 10, am I right? Okay. Take 37 apples from 100 apples. How would I write that? 100 minus 37. Very good. How about if I said this? Subtract 12z from 20z. Now I'm trying to get a little tricky on you. How will I write this? 20z minus 12z. Are you guys seeing a trend here? When they say remove something from something, this item here then is the first item in that subtraction problem, also called the minuend. Okay? Be very, very careful as we embark on this adventure, because I guarantee you I'm going to go back to dollars, apples, and z's for you when you mess these up, because it's just an easy thing to trick up. Example 5. Here's example 5. Subtract 2x squared minus y squared from 5x squared plus 7xy plus 2y squared. Okay. Which thing gets written first? The second thing. And it's going to look like this. 5x squared added to 7xy added to 2y squared. Okay, there's that first component. And I am removing this component from that. There's a reason why I'm using this parentheses and this red. Recognize this entire piece is getting removed from that previous first piece. What do you think that means about the negative sign with respect to these two items? Anybody have any ideas how you can make this easy on yourself? If you are subtracting this from that, use the distributive property and distribute the negative value over those two pieces that are being subtracted, which makes it look like this. Now you can simply bring down all of the other pieces and combine them now that you have, in effect, flipped the sign of everything in the subtrahend. This is a huge area of mistake. I see it every year. When you are subtracting, identify the piece being subtracted, as I've done here using parentheses. Distribute the negative sign, therein flipping, and once you've flipped, you can combine like terms. So, our x squareds, 5 and negative 2, looks like 3 of them, am I right? XY, they stay the same. There are none to be removed, or there are none to deal with. And y squareds, 2 and 1. Was there anything else? Nope, that's it. By the way, that's an easy mistake to make too. Somehow you forget to copy something, you forget to bring down the little squared symbol, whatever. You know you're done when nothing else can be combined. Guys, if there was ever an area that you could foul up, it's this one right here. So be mindful of that. Practice that for sure.